A 4.0 kg block extends a spring by 16.0 centimeters from its unstretched position. The block is removed and a 0.5 kg body is hung from the same spring. If the spring is then stretched and released, what is the time period of oscillation? So let's try to understand what we are being asked in the question. So in the question they're saying there's a spring, and on this spring we have a 4.0 kg block. Now upon hanging this block to this spring, this block has 4 kgs in terms of mass. So this block simply extends the length of a spring to 16 centimeters from its unstretched position. So upon placing 4.0 kgs block of mass, the length stretches to 16.0 centimeters. All right. So from here, what comes after this is that the block is removed. So upon removing it, we then replace it with another one, which is 0.5 kgs. So after removing the 4.0 kgs block, we then hang a 0.5 kgs body to the same spring. So now what we're told to find is, if the spring is stretched, that is with the second mass, which is 0.5, and released, what is the time period of that oscillation? So the 16.0 centimeters is the length obtained after hanging a 4.0 kgs. So now with the second mass, we are not given the actual length, but what we just note it is stretched and released. So with this, we are supposed to find the time period of oscillation. So we need to note that time period. Okay, let me use a different pen color. So go with black. So we say that the period, as we know it, is calculated as 2 pi over angular frequency. So the period we're finding is after stretching the spring upon hanging this 0.5 kgs body. Now if you look at this, angular frequency is not given, but in a case where angular frequency is not given, we can also calculate the period by saying 2 pi m divided by k under a square root. Now if you look at this, the mass is given to be 0.5. We aren't given the spring constant. Now we need to find the spring constant. So from what we know is that, or from the formulas that we've generalized in our lessons, we have that K is equals to K is equals to mg divided by the length. All right, so here the length we have is not for this block, but for this one. It's not for this mass, but for this block, which is 4.0. But what you know is that no matter how you stretch a spring, its constant will still be the same. So despite us having changes with the masses, we still have the same spring constant. That is to say, even if we use this mass together with its length, the constant will still be the same as when we use this mass with its length. So we now have that K is equal to, the mass is 4.0 we are using, since that's the unit length, then multiply by 9.8. Then what we do, we divide this with the length. The length we have is simply 16.0 centimeters, and converting this to meters, which is a standard unit, we get 0.16. Okay, so now we're going to do the mathematics and see what we're going to get. All right, so now let's use a calculator. 4.0 being multiplied with 9.8, then this altogether be divided with, okay, so let me do this. We have something like this. We have 4.0 multiplied by 9.8, then we divide this with 0.16. so the answer we are getting is 245. All right, so 245 is our spring constant. So K is equals to 245 Newton per meter. Now, since we've obtained the spring constant, we can come here and say that T will now be equals to 2 pi, which is the same as 3.142, multiplied by the mass. We are now using this one for 0.5 since we are obtaining the period of oscillation for this particular mass upon stretching it. Okay, so we have upon stretching the spring, so we have the mass which is 0.5, then we say over 245. Okay, so let's do calculations again. So we have 2 multiplied by pi, this is multiplied by the root of, we can do this, there we have 0.5, then we have 245. Okay, all right, so okay, so in decimal notation, this is the same as 0.283. All right, so that's our answer. Have period to be equals to 0.283, and the units for these are seconds, and then we are done with our question.